Alright, by the way, in this video you might hear some banging, and that's because they're doing construction outside. Oh, also, by the way, it is 12:43 a.m. I don't know who gave the okay for construction to be going on after midnight, but it's been going on for the past week or so, and it has not been fun. But, anyways, at least it helps me stay up so that I can do math problems instead of getting good nights of sleep. So anyways, suppose AI is not contained in P for I between 1 and n minus 1. So we're going to assume that P, I guess I should have started by writing again. Suppose that P is contained in, yeah, you know what? I'm going to do that. I feel like I've been writing these pretty sloppy, just because I feel like if I can explain something out loud, then that's faster than writing it. But, yeah, so it might, I don't know. I guess what I'm saying is that the way that you should write these, or that you should, like, if you're writing out a proof of one of these exercises, you shouldn't go, like, necessarily word for word what I'm writing, because when I'm writing, I'm leaving out a lot of stuff that I'm just making comments on, and it might be better to include those comments in writing. But I mean, I'm handwriting this, and that takes a long time. It's much easier or much quicker to say something than to write it. So, for the sake of time, I leave a lot of details out. So, suppose that P contains this, and then I'm going to suppose that. So we want to prove that P contains some AI. So suppose that, here, let's write it this way. Suppose P does not contain AI for I between 1 and n minus 1. So we want to prove then that P contains an, because if it doesn't contain any of the others, to prove that it contains one of them, it suffices to show that if it doesn't contain all but one of them, then it must contain the remaining one. And so I guess, yeah. So if P contains if P contains A1, A2, or any of those all the way up through AN minus 1, then we're done. Otherwise, we're going to prove that P contains AN. Okay, so suppose that P does not contain AI for these I. Then for all I between 1 and n minus 1, there exists an AI in capital AI set minus P. Because if this weren't true, if some AI did not have such a, if some capital AI set minus P did not have such an element, little AI, then that would imply that that particular AI is contained in P, which is not what we're supposing. Then for all AN in capital AN, we have that the product A1 times A2 all the way up through AN is going to be in the intersection from 1 to n of AI. And that's because so if we look at, if we fix AJ, then A1 through AJ through AN, this element, this is just we know AJ is an element of capital AJ, and we're just multiplying this on the left and right by other elements of the ring, and since capital AJ is an ideal, we know that this element is contained in capital AJ. But this holds for every single j between 1 and n minus, this holds for every j between 1 and n. And so that means that A1 through AN, that this product is going to be contained in every single AJ, which means that's going to be contained in their intersection. And so, of course, this is contained in P. So the product A1 through AN is contained in P, but P is a prime ideal. So since capital P is prime, and this is just, we're using the primeness condition for ideals, but generalized to n products. So typically we have AB in P implies that A is in P or B is in P. But more generally, if we have A1 through AN is in P, then A1 or all the way up through or AN is in P. One of these factors is in capital P, and that's just from that's just a simple induction proof. I'm guessing or hoping that they mention that in the text, but if they haven't, it should be fairly easy to see that. So since P is prime, we know that little ai is in P for some I. Let's see here. We know that for j between 1 and n minus 1, ai or aj is not in P by choice. Thus an must be in P because that's the only one that's allowed to be in P. Now this holds for all little an and big an, and hence capital AN is contained in capital P. So there we go. Therefore, P contains AJ for some. Okay, I guess these should be I's. Therefore, P contains AI for some I because it's either going to contain some AI for I between 1 and n minus 1, or if it doesn't contain any of those, then it has to contain the last one. So there we go. So that's the first part. Okay, so now if P equals the intersection from 1 to n of AI, then P contains AI. I can't close my A's for some reason. And P contains AI for some I, because we just proved that. And P equals the intersection from 1 to n of AI, which is a subset of this particular AI. And thus, we have P contains AI, and P is a subset of AI, and thus P equals AI. And so there we go. That's the last part of the proof, and so we're done.